Welcome to the Material Science Laboratory. In this presentation, we will abort tensile, compressive, and hardness test. For this presentation, we have three main objectives. The first one is perform a destructive tensile test on a metal specimen and interpret the data. The second, perform a destructive compress test on a concrete material and interpret the data. And finally, perform a non-destructive rock-wall hardness test and interpret the data. All materials work in different conditions. These conditions can affect the material's performance, and it's important to consider that one important condition is the temperature. Therefore, after to participate in these experiments, you will learn the correlation between the rock-wall hardness value and the tensile strength, and the impact of the temperature on the mechanical behaviors of the materials. Background. Let's start with the tensile test. Tensile test is fundamental to understand the behavior in material mechanics. It is performed by pulling a sample of material apart until the failure, while measuring the force and the displacement. As example, we observe a metal sample in tensile test. The two flashing blue arrows represent the tensile forces acting on the sample. In tensile test, the force and the deformation are data provided while the experiment runs. Since we have force and displacement, tensile tests will provide us with something called a stress-strain curve. The force and the displacement are related with the sample tested. Just remember, the actual forces can be transferred along the sample. Let's think if we apply a tensional force at the extreme of each of this sample. If we cut the sample and we could observe internally how the force is acting, we find out that the force is distributed on the complete area of the cross-section. Then, the stress is equal to the applied force over the corresponding area. Now, let's see what happened about the length. The dimensions of a sample will be affected by the applied force. Since we produce tensile at each extreme of the sample, the expected information is an increment of my original length. This increment, delta L, divided by the original length is called strain. Tensile testing provides one of the most widely used tools in engineering to describe the behavior of materials. This is the stress-strain curve. As the stress rises, the material begins to deform, and the initial linear region is elastic deformation. That means this specific part of the deformation is recoverable. If we remove the force, the material can return to its original shape. The slope of the curve within the elastic deformation gives Young's model and is represented by E in capital letters, which is a measure of how stiff the material is in the elastic deformation, which can be expressed as stress over strain. The end of this linear elastic deformation is marked by the yield point. In many cases, the exact yield point cannot be easily identified. By convention, the yield point is defined as the intersection point of the stress-strain curve with the elastic linear line shifted by 0.2% on the x-axis. From yield point, any additional stress will cause permanent deformation. This is called plastic deformation. as the stress continues to rise until it hits the ultimate stress point. This is the ultimate stress, the most stress material can handle. From here, less stress is needed as the sample starts to develop necking, which reduces the cross-sectional area. This continues until the material fractures. For describing the material behavior, we measure the ductility. As a measure of the ductility of the material, the percentage of area reduction at the fracture region is used as the showed equation, where AF is the cross-sectional area of the fracture region, or neck, and A0 is the initial cross-sectional area of the sample. Compression test. Compression test is another type of fundamental mechanical testing, alongside tensile and bending test. Compression tests are used to determine a material's behavior under applied crushing loads by applying compressive pressure to a test specimen. Compression testing is often used on brittle materials such as concrete and ceramic. The forces we apply on the sample, as can be expected, will be a shortening of the original length. These materials are often used in loading bearing capacity where the integrity under compressive forces is critical. The ultimate compressive strength of a material is the value of compressive stress reached when the material fails completely. When brittle materials reach their ultimate compressive strength, they are crushed and the load drops drastically. Hardness test. Hardness can be defined as the property of a material that enables it to resist plastic deformation, usually by penetration. Hardness is related to resistance to bending, scratching, abrasion, or cutting. And the most common method to determine the hardness is the Rodwell hardness method. Rodwell hardness method consists of indenting the test material with a diamond cone or hardened steel ball indenter. The indenter is forced into the test material under a preliminary minor load F0. When equilibrium has been reached, it is set to a datum position. While the preliminary minor load is still applied, an additional major load is applied, with resulting increase in penetration. When the equilibrium has again been achieved, the additional major load is removed, but the preliminary minor load is still maintained. And again, when the equilibrium has been reached, is set to a datum position. Obviously, we are interested in the both positions, the initial and the final. Removal of the additional major load allows a partial recovery, so reducing the depth of penetration. The permanent increase in depth of penetration resulting from the application and removal of the additional major load is used to calculate the Rodwell hardness number. Advantages of this method include the direct Rodwell hardness number readout and rapid testing time. If there are advantages, there are disadvantages as well. For example, many arbitrary and non-related scales and possible effects from the specimen support anvil. Please check the Rodwell HRV harness strength table for the steel materials that you have in your document. Temperature. Temperature is an important condition for the behavior of materials. Let's see, as an example, the case of the metals. Generally, metals become weaker and more ductile at elevated temperatures and become brittle at very low temperatures. This stress-strain diagram shows the behavior of a low-carbon steel at different temperatures. The red curve is at 23 Celsius and the blue curve is at -40 Celsius. With the graphic, it's easy to realize that the sample tested in dry ice bath conditions show higher ultimate tensile strength, but lower strain at failure. This is due to the behavior of atoms. At higher temperatures, atoms move more easily than at low temperatures. About the theory, the final comments are: first, materials exhibit high yield and ultimate strength at low temperatures. Second, for composite materials, the effect of the temperature on the strength of the material could be quite different. Third, as a concrete material always contains water, a temperature below the freezing point could turn the liquid water into ice. In this case, the ice could behave as an extra of reinforcement material give concrete more strength. Experiment steps and procedures. For the experiment, you must measure the dimensions of the samples as well as the loads that you apply to each sample, concrete or metal. Obviously, that information must be recorded as data from the experiment and also perform some calculation based on the mentioned equations. The first step is to measure the dimension of all the samples that we have, concrete or steel, and later to calculate the area of the cross sections. Measure the Rodwell hardness values of the tensile samples and use the conversion table to convert the hardness value in tensile strength. Remember to use the calibration block to check the calibration of the hardness tester before the test. Perform tensile tests for the tensile samples at room temperatures and dry as bath temperature conditions. Export the CSV files from the computer and use the Excel to create the stress-strain diagram using equations 1, 2, and 3 for each of the samples and calculate the values of E, yield strength, and ultimate strength. Measure the cross-section area at the neck and calculate the percentage of reduction using the equation 4. Finally, perform compression tests for the concrete cylinder samples at room temperatures and dry ice temperature conditions.